Hi everyone, I am Zishan Jadun from Photonics Engineering Department, Chosun University. In this study, we analyzed mechanisms of transformation of electromagnetically induced absorption and transparency resonances at D2 lines of rubidium-85 atoms. We solve optical block equations with and without neighboring hyperfine states near the degenerate two-level system in the challenging case of 85 rubidium D2 transitions that involves Doppler broadening effects. The mechanisms of electromagnetically induced absorption and transparency at the open transitions such as 3 to 2 and 3 to 3 or 2 to 2 or 2 to 3 are clearly determined to be the effect of strong closed transitions such as Hg3 to 4 and 2 to 1 transitions of 85 rubidium atoms. The calculated spectra agree well with the experimental results obtained using the coupling probe schemes with the orthogonal linear polarizations of coupling and probe fields. The crucial factors established based on the comparisons of the calculated absorption profiles of DTLS with and without neighboring states, which enhance or reduce coherence effects and result in transformation between EIA and EIT, are the power ratios between the coupling and probe beams, openness of the excited state, and effects of the neighboring states due to the Doppler broadening in a real atomic system. Energy level diagram of D2 transition line of 85 rubidium atom are presented in figure 1. The coupling and probe beams that are linearly polarized with orthogonal directions propagate in the same directions. Because the energy separation between the hyperfine states in 5s half ground state is approximately 6 times the Doppler line width of the atoms, we can calculate the EIA spectra for the Fg3 to 2, 3 and 4 transitions and 2 to 1, 2 and 3 transitions separately. Theoretical calculations are solved utilizing time-dependent density matrix equations. In a frame rotating with the coupling beam's frequency, the density matrix describing the internal dynamics of the atoms is given by equation 1, where ρ is the density operator and H0 and V is the atomic and interaction Hamiltonian, while relaxation mechanisms such as spontaneous emission and transit time decay are represented by ρ.relax term. The density matrix elements responsible for the probe absorptions are given by equation 2, and the absorption coefficient of the probe beam is expressed in equation 3. The coupling and probe beams are generated using a single laser combined with 2 EOMs in a single pass configuration as shown in figure 2. A combination of half-wave plate and polarizing beam splitter 1 controls the ratio between coupling and probe beam intensities and polarizations. The probe and coupling beams are linearly polarized with orthogonal directions and expanded by 5 times to obtain a uniform intensity across a 4 mm diameter. The probe frequency is logged utilizing a saturation absorption spectroscopy setup. Figure 3 presents comparisons of calculated spectra, that is, with the resonant transitions shown in figure A, considering all neighboring transitions shown in figure B, and experimentally obtained spectra shown in figure C. It can be noted that calculation considering only resonant transitions satisfy all EIA and EIT conditions, displaying a strong EIA resonances at closed 3 to 4 transitions and weak amplitude EIT resonances at open 3 to 3 and 3 to 2 transitions. While both experiment and calculation considering all neighboring transitions predict EIA spectra is similar in amplitude, while at higher intensity of coupling, the EIA spectra splits at the right center. Similarly, comparison of calculated spectra for transition lines 2 to 1, 2 and 3 is shown in figure 4 with pure two-level transitions at shown in figure A, with all neighboring transitions shown in figure B, and experimentally measured spectra for resonant transitions shown in figure C. The sign inverting anomalies present at open transition 3 to 2 and 3 in the previous case, as shown in figure 3B and C, are not relevant to 2 to 1, 2 and 3 group of spectrally resolved transitions, as the EIT resonances are at 2 to 3, 2 and 1 are expected. Instead, anomalies in relative strength of amplitudes and line weights are evident in calculation and considering all neighboring transitions and in experiment, as shown in the load traces of figure 4b and 4c respectively. In this study, we deduced that clear explanation for the transition of EIT into EIA in the case of rubidium-85D2 transitions can be obtained based on comparisons of calculated absorption profiles of degenerate two levels with and without neighboring state. Coherent spectral profiles calculated by considering all neighboring high-profile levels clearly determine the sign of EIA and EIT resonances compared with the experimentally observed spectra. This phenomena had remained theoretically unexplained and not been observed previously in the case of 85 rubidium D2 lines. Thank you very much.